having me. So as Phoebe said, I'm an postdoc here, working on sort of these broad questions. The title for today's talk is Connecting Pattern and Process Through the Use of Remote Sensing in Forest Ecology. So this is kind of a broad term that encompasses both my dissertation research as well as some of my current research here and some research that we're going to be focusing on in the future. So the overall question that I asked of both my dissertation research and my current research here is, how does landscape heterogeneity influence ecosystem functioning and biodiversity? So in terms of my dissertation research, I was focused more on how climate interacts with disturbances. Sorry. But now I'm shifting more into how landscape heterogeneity influences more specifically biodiversity, so these more biotic aspects of ecosystems. So what do I mean when I'm talking about environmental heterogeneity? Primarily here, I'm focused on geodiversity, or the variation in Earth's abiotic processes and features. This can include anything from topographic variability, so for instance, mountain landscapes versus plains, things like variability in soil age or soil classes, or variability in hydrologic features. However, I'm also interested in variation in climate and productivity as well, and how that interacts with ecological processes. So as I mentioned, today I'm going to be talking a little bit about my dissertation research. Most of my time is going to be spent on that, and specifically these two questions. The first of which is, how does local environment affect disturbance impacts? So this question is mostly focused on how disturbance impacts vary across ecoregions and also among disturbance types, and I use remote sensing data to answer those questions. And then a lot of my dissertation research was looking at these very large-scale patterns of disturbances, so I got really interested in this question of how do we actually detect and attribute forest disturbances using remotely sensed data. So my second portion of the talk here is how do landscape characteristics influence our abilities to detect disturbance events. And then the last thing I'm going to talk about today is this question of how does variability in the abiotic environment affect current and future levels of biodiversity. So this is some of our current research here. I've only started on this a little bit, but I'll present some preliminary data. Alright, so just a refresher for those of you who haven't thought about disturbances in a while. A disturbance is defined as a relatively discrete event in time that disrupts the ecosystem, community, or population structure and changes the resources, substrate availability, or the physical environment. So today I'm mostly focused on disturbances in the western United States. This can include things like forest fires, bark beetle outbreaks, or events like windthrow or landslides. So why do we care about disturbances? Mostly I'm interested in disturbances not only because I grew up near Idaho, so we experienced a lot of forest fires out there, and it's kind of this constant presence, especially during the summer. But also, the more I learned as I continued my career was that disturbance really impacts pretty much everything having to do with ecosystem functioning. So this is sort of a classic idea of disturbance here. You have these patches on the landscape that are disturbed, and those patches are going to differ a lot from the healthy vegetation around them. So this can influence everything from genetic variability on the landscape to things like climate and the ways in which species interact. So one of the papers that's kind of cool here is this paper by Lake in 2000 that was focusing on freshwater ecosystems. So this is really cool because it connects disturbance patterns to both productivity in the ecosystem and then up that chain through to biodiversity. So what they saw here was as you increase frequency and severity of disturbances, you get a decrease in productivity of these systems. So for instance, as you increase the frequency of extreme flow events, you get a decrease in the productivity of the stream. This is important in its own right, but it's also more important for the cascading impacts that that has on the ecosystem. So not only are you influencing productivity, but then that productivity has the potential to influence biodiversity or species richness down here on the bottom. So what they saw was that moderate levels of productivity in the system correspond to these really high levels of species richness. So this is the idea that if you have moderate levels of disturbance frequency or intensity, you can actually have very large impacts on species richness and all sorts of other ecosystem processes. So this is really interesting on the biotic side of things, but some of our more recent work has actually focused on the abiotic side of things. So disturbances not only influence things like biodiversity, they also influence things all the way down to the radiative budget of the system. So this is a paper that I worked on with some colleagues at University of Montana. And this is looking at the effects of forest fires in several biomes around the globe on radiative forcings of the system. So here we're looking at boreal forests versus tropical savannas, and then LST, which is land surface temperatures on the top, shortwave radiation in the middle, and latent energy, which is essentially the amount of energy in the system that goes towards changing the phase of water. So what we see here is that not only can disturbances have very strong influences on these radiative budgets, so we see really sharp increases in surface temperatures and also declines in shortwave energy and the latent heat of the system, but these impacts really differ across ecosystem types. So you're not going to have the same impacts if you're looking at a boreal forest following a forest fire versus a fire in a tropical savanna. So this is the idea that kind of drove this first chapter of my dissertation, which asked the question, how does the local environment affect disturbance impacts? So again, we see this across biomes, boreal versus tropical savannas, but we also see this just within ecoregions in the US. So for example, a fire in a desert ecosystem is not going to have the same impacts on the radiative budget or biotic interactions, for instance, as a fire over here in the northeast. So the landscape in which the disturbance is occurring really impacts the impacts that we're going to see. So this is really important because we need to be able to predict what fires and other types of disturbance are going to, what impacts they're going to have on landscapes so that we can manage forests for the future. But little is known about how these disturbance types compare both across ecosystems and disturbance types. The last part of my dissertation was focused on detecting and attributing forest disturbances using remote sensing data. So the question here was, how do these landscape characteristics influence our ability to detect disturbance events? So the idea here is that variables that let you know if a disturbance occurred are not going to be the same depending on the ecosystem that you're looking at. So for instance, this more populated area over, I think this is in South Carolina, is not going to have the same sort of disturbance characteristics as a system over in Oregon, for instance. So, for instance, over in Oregon, things like the magnitude of disturbance or like the drop in greenness are going to be really important for locating that disturbance type, whereas over here it might be the variability in the landscape. All right, so just to jump right in here, the first chapter I'm going to be talking about is how do disturbances influence surface temperatures and carbon uptake across ecoregions. So the basic idea here, sorry, slides got very messed up. The basic idea here is that you're going to have changes to both the carbon cycle and the energy and water cycles, all in disturbances. So in terms of the carbon cycle, if you think about healthy vegetation, there are a few basic processes going on here. Forests take up carbon through the processes of photosynthesis and release carbon through autotrophic respiration or decomposition. But if a fire occurs in that landscape or any other disturbance type, you're going to get changes in those processes. So for instance, if you remove healthy vegetation, you're going to get decreases in photosynthesis as well as autotrophic respiration, but you're going to get a big pulse of carbon released from the atmosphere, released to the atmosphere, either through the processes of combustion or decomposition. All of these changes combined can lead to decreases in the uptake of carbon by the system, so you get these decreases in primary productivity. In terms of energy and water, you see similar changes here. So in a healthy forest, you're going to get radiation absorbed by the surface depending on its albedo or reflectivity, and some of that radiation will also be reflected. Additionally, you're going to get a release of water to the atmosphere through the process of evapotranspiration. However, when a disturbance occurs in this system, you're going to get potentially, we'll say it's a fire, so you might have charring of the surface, lowering the albedo, and you might get an increase in the absorbed radiation of the total energy absorbed by that system, and less reflected radiation. Additionally, because you're removing vegetation, you're decreasing the amount of evapotranspiration from the forest, so releasing the amount of water present in the area. All of this combines to affect both the latent heat flux and the sensible heat flux. So just a reminder again, latent heat flux relates to the amount of energy going into changing the phase of water, whereas sensible heat flux is what you can measure with just a thermometer or something. All this combines, both the increased absorbed radiation and the decreased amount of energy going into this latent heat flux, combines into an increase in surface temperatures. Okay, so a lot of research has actually looked into these impacts. However, a lot of this research has looked into very large and severe disturbance events, such as this very large outbreak of mountain pine beetles in British Columbia. So if you're not familiar with what a mountain pine beetle looks like, it's this little guy up here. They're actually only a couple millimeters or so, a few millimeters in size. But they can cause this massive damage. I don't know if you can see this, but all of this forest is red. So it's pretty much entirely affected by this mountain pine beetle and will convert into this gray stage or just dead vegetation within a couple of years. So the research looking at this has looked into both carbon impacts of these extreme disturbance events as well as the effects on the radiative budget. So one of these big papers was published by Kurtz et al. In 2008 in Nature, and this is looking at the carbon effect of these mountain pine beetles on these forests in British Columbia. So what we see here on the y-axis is ecosystem carbon stock change, basically carbon uptake of the system, and then over time. So these are 3 modeled scenarios. One of them is a control scenario without bark beetles, and 2 of them are with the bark beetles. So what we can see is that without the bark beetles, this forest remains a carbon sink, as it is a net uptake of carbon from the atmosphere. However, with these beetle scenarios, you actually see a net release of carbon to the atmosphere from the forest. So these can have very large impacts and very long-lasting impacts on local or regional climate. Similarly, the study by Manasse et al. In 2013 looked at the same area in British Columbia, but now they're actually looking at evapotranspiration here on the top and changes in the difference between daytime and nighttime temperature on the bottom. These different colors correspond to different severities of the pine beetle outbreak. So what we see is that you can also, in addition to these big carbon impacts, have very large impacts on evapotranspiration and temperatures in this ecosystem. So again, these very large and severe disturbance events can have very real impacts on regional climates. However, what we wanted to look at was what happens if you decrease the severity of that disturbance. Are you going to see these impacts? Are they going to remain the same? And also, how do they relate to different disturbance types? So are you going to see the same impacts following pine beetle outbreaks versus fires versus wind throw events? So to that effect, we asked these 3 questions. First of all, how do surface temperatures and primary productivity change following disturbances in forests of the western United States? So just looking at these changes in carbon uptake and temperatures. Also, how do those impacts differ according to ecoregion and disturbance type? And then finally, how are those impacts affected by the severity of the disturbance and then the extent or total disturbance area? So we asked this 3rd question here with the idea that because disturbances are increasing in frequency and severity as temperatures warm and climate changes, if we see severity as a very strong feedback with these disturbance impacts, then you might see very real increases in the disturbance feedbacks of climate in the future. All right. So in order to do this study, we really wanted good fine resolution maps of where disturbances are in the landscape. So currently we have all these polygon products that tell us approximately where a disturbance is located on the landscape, but that assumes that all of the area under those polygons is disturbed. So we wanted to actually look at a finer resolution and not get healthy vegetation when we're only interested in disturbed vegetation. So in order to do this, we use remote sensing data, and specifically the MODIS Enhanced Vegetation Index, which is just a satellite measure of greenness of the vegetation, essentially. We looked from 2000 through 2014, and these data are at 250-meter resolution. In order to locate disturbances on the landscape, we used a change detection approach, and specifically this breaks for additive season and trend change detection algorithm. So the way that this works is essentially you have greenness here on the y-axis over time, so you have these time series of disturbance, but they're really messy. So in order to actually figure out if there are breaks in that time series, you have to decompose it. So all this VFAST algorithm does is it breaks this very messy trend into 3 components. So first you've got the seasonal component, so just the difference in greenness between, say, summer and winter. And then you have this main trend component, where you can see these now very clear breaks in the time series. And then finally, you just have the remainder or noise component. So here, indeed, BFAST found 2 disturbance events in this time series. So now we have this map of disturbance, but we don't know what those disturbances are. So in order to actually attribute the disturbance types, we did end up using these polygons that I mentioned before, and just overlaid them on this map of disturbance. So in order to find fires, we used monitoring trend and burn severity, and then for bark beetles and foliating insects, we used aerial detection surveys, which are just a product from the Forest Service. And then finally, we didn't really have these good polygon products for any of the other disturbance types, so we had to lump them into this unidentified disturbance category, which was primarily made up of harvest, but there were some of these smaller scale disturbances lumped in there as well. Alright, so this is a map, I should note that it is very much so not to scale, of where these disturbance events are in the western United States. So you can see that you have bark beetles kind of all over in these drier regions of the west. You have the foliating insects towards the north in these wetter regions, and then fires kind of scattered all around. Again, most of this gray stuff over here, the unidentified disturbances, is harvest. It's a very big disturbance over here in the Pacific Northwest. Alright, to dive into results, I'm just going to show you one figure at a time, and then we'll look across different disturbance types. So what we're looking at here is the change in surface temperatures, which were measured, again, using MODIS data, so a remotely sensed product. So you have an increase in surface temperatures indicating a rapid change here. And this is years since disturbance, starting 2 years before the disturbance and ending 12 years afterwards. And this is changes over the entire western United States, not looking at the ecoregional differences. I should note that these different colors correspond to different severities of disturbance, with pink being the highest severity and green being the lowest severity. And we measured severity as a percent decline in EBI, which actually corresponds very well with severity maps. So what we see here is you actually do get a pretty big increase in surface temperatures following disturbance events. And this is pretty consistent when you look at these other disturbance types as well. The interesting thing here is you actually get pretty sustained differences in surface temperatures following pretty much all disturbances, but especially fires here, and especially high severity disturbance events across the board. Okay, so shifting gears to look at gross primary productivity, or GPP. Again, this is carbon uptake. This is the same figure, except now we're looking at the percent decline in GPP, post-disturbance relative to pre-disturbance levels. And we see pretty sharp declines in GPP as expected. One interesting thing to note here is that in these lower severity disturbances shown in green, you actually see some of these error lines overlapping 0. So this indicates that there were some areas of the landscape where you actually see slight increases in productivity following bark beetle attack. And what we think is going on here, we're not sure, this might just be an artifact of the remote sensing product, gross primary productivity, because it is a modeled product. However, we did a separate dendrochronological study looking at forests after bark beetle outbreaks, and you do see a growth release in some instances. So it might be that low severity disturbances are actually decreasing forests from competition for water and resources, and you actually can get slight increases in productivity following these events. So this is something I'd kind of like to look into a little bit more. And again, when we look at these other disturbance types, you see pretty similar patterns. And especially, again, severity seems to be a pretty big controller of the degree to which you see a decline in primary productivity. What I'm not going to show here is that we actually did this for every single ecoregion, so 9 ecoregions covering the western United States, because we wanted to look at these ecoregional differences. And we did see different patterns according to ecoregion. So in some areas, these differences were really high pre to post disturbance, some of them were very low. So it really does depend where you're looking, what typical disturbance patterns you're going to see. All right, so the last thing we wanted to look at here was how important are severity and extent to these impacts of disturbance. So here we used a mixed effects model to look at the importance of severity and disturbance area. And what we found was pretty intuitive, especially if you've looked at the results that I just showed. And severity is the primary control over surface temperatures and primary productivity. So essentially what we're saying is that if you have a very small disturbance event, say a very low severity fire, you're going to get very small impacts on both GPP and LST, whereas if you have a very large fire, you're going to get very large impacts on those same variables. So this is extremely intuitive, but it is interesting in that, as I mentioned before, severity is predicted to increase, so we will start seeing these much larger influences on feedback to climate from disturbance events. All right, on a larger scale, again, this is some work that I've done with collaborators at the University of Montana. We looked at fires globally, shown over here, and we looked at this same question. So how do fire area and severity of fire influence surface temperatures, shown here on the Y? And what we saw is pretty much the same thing that I found on that smaller regional scale. So severity is a very large controller of how big that change in surface temperatures is, whereas you really don't see much of a pattern when you look at the percentage of area burned. And these two different colors here, this is again boreal forest, and the right is tropical savannas. Okay, so in conclusion for this study, we did see strong potential climate feedbacks due to all different kinds of disturbance impacts, but this was primarily controlled by the severity of the disturbance. So again, you might see increasing feedbacks to regional climates or local climates as severity of fires and frequency of fires and other types of disturbances increase. However, we weren't really able to get a lot of these lower severity or smaller disturbances in our data set like we were hoping. And a lot of this is that these change detection approaches are either oversensitive or not very sensitive, and then also we have a lot of trouble figuring out what those disturbances actually are once we've identified them on the landscape. So I wanted to look at this a little bit more in this next study I'm going to talk about, with the question of how can we improve our abilities to detect and attribute forest disturbances. So again, just a refresher on what previous methods have done here. Imagine that this is a forest with a raster over top. So here this is showing, you can't really see it in this light, but there's a forest fire back here. This is in Olympic National Park over in Washington. And what most disturbance detection algorithms do is they take one of these pixels, such as the one highlighted here, and they look at the change over time in something like greenness. So for instance, if you have a forest fire occurring in this pixel, you're going to see a pretty sharp decrease in greenness, as shown here. But the problems with this are what happens if you change the background or the type of landscape that you're detecting that disturbance on, or you change the type of disturbance. So for instance, if you have a not very green background, so for instance a desert ecosystem, that blip in greenness might be much smaller and much more difficult to detect using this single pixel approach. And then also, if you have something like bark beetles that are occurring over many, many years, that's going to be much more difficult to detect because it's a gradual decline rather than a very, very sharp decline. So one of the things that we wanted to do is take the single pixel approach and make it a little bit more complicated by using some of the other information that's available in these rasters. So not only are we looking at the single pixel, but we also want to look at the surrounding environment. So there's a lot of information in that surrounding environment that we're actually losing by just looking at one pixel at a time. So in order to do this, we decided to use a very basic machine learning algorithm, just random forest modeling, which is essentially a consensus of a bunch of different decision trees. So this is really useful because it's really straightforward to use, but also it can take a lot of different variables. So we can throw in lots of different time series variables, but also lots of these different variables that indicate the spatial environment in which this disturbance is occurring. Okay, so to break this down a little bit more, again, most disturbance algorithms, when you're just looking at this change detection approach, are going to be looking at single pixels. For instance, this pixel highlighted in gray here. So when we look at this approach, you can look at a few different variables. Some common ones are, for instance, the magnitude of disturbance, so the drop in greenness following the disturbance event. Things like the duration of the disturbance, or the length of period of time that that greenness is declined, or things like the rate of increase following the disturbance event, or the rate of recovery. But again, this is just for one pixel. So what we wanted to do was add in spatial information. So these two variables on the right, we did two different models, one for detection and then one for attribution. So for detection, we added in these things that I'm deeming spatial variables. So this is essentially taking these things, rate of recovery, magnitude, and duration, and summing them or summarizing them over this entire gray area rather than just a single pixel. And then once we get these detection estimates, so we know approximately where disturbances are in the landscape, we can then look at the spatial patterns of those pixels individually. So we can take those pixels that are supposed to be disturbance and look at these same summary variables. So the average magnitude of the disturbance pixels, or the average rate of recovery of those disturbance pixels, and that should give us a hint as to what the disturbance actually is and if it's a true disturbance. Okay, so we applied this model over 7 Landsat scenes located across the United States. So some in the West, 1 in the Midwest, and then 3 on the East Coast. I chose these because they match well with some other studies that have been done, so we can compare our accuracy with those studies as well. And the basic methodology here is that we pre-processed Landsat imagery, so this is satellite imagery at 30-meter resolution. We calculated NDVI, or Normalized Difference Vegetation Index, which again is just a measure of greenness. We removed clouds and any sensor errors, and then we input this data into R for the remainder of the process. So in R, we created a detection model to find potential disturbance events using a random forest model, and then we created a secondary random forest model to attribute those disturbances, and also to hopefully remove some false positives. And then finally, we get our product here, which is maps of both disturbance type and the year of disturbance. Okay, just looking a little bit more at this. This is one of those squares that you saw in the previous slide. In order to do this in a computationally reasonable amount of time, I decided to break this up into 9 blocks per scene. Okay, and then I created these random forest models. So I trained those those models on random points, about 600 points, located across these 3 blocks in the diagonal. I decided to do a diagonal rather than just a pure random sampling of blocks because it covers more of the Landsat scene. So hopefully we get a good distribution of disturbance types and the like. I then applied both these models, the detection and the attribution models, to the entire Landsat scene, and then validated on samples from an additional 3 randomly selected blocks. Alright, so these are some preliminary results. So here we're looking at the model accuracy. The overall accuracy was between 59 and 97% accurate, with a mean of 75% and a median of 77%. So here on the y-axis, I'm showing false disturbance rate, which is just the disturbances that were labeled as disturbance that were not actually disturbed pixels. And then on the x-axis, we have the misdisturbance rate, or those pixels which were labeled as undisturbed but were actually disturbed. So these results look pretty good to me, in that we really want these misdisturbance and false disturbance rates to be very low. Most of them are pretty low, and we want them to fall on the diagonal. So the worrying thing here is that we do tend to get this kind of creep up the y-axis. So this indicates that we're getting a lot of false disturbances. However, I should note that our validation is not done yet. So these are just preliminary results, and I need to do some more intensive sampling to make sure that we actually are seeing this pattern and that this isn't just an anomaly. However, these rates are pretty good, and they're pretty comparable to other studies. So for example, the vegetation change tracker algorithm by Hong et al. In 2010 has accuracies falling within this circle. It varies because they looked at this across several different ecosystem types, not just one. And then Cohen et al., who have this sort of new method where they apply a change detection method to several different satellite indices and then do a random forest model to get a consensus of those, falls in the about 30% false disturbance and 30% misdisturbance rate. So this is pretty comparable to those studies. It might be a bit better, it might be a little bit worse in terms of creep up here, but overall pretty good. And I should note that this is especially good because it's pretty consistent across these 7 Landsat scenes. So I'm happy with that. Okay, so the other map that we made was looking at the year of disturbance. So these are the accuracy results for that. So here we've got the proportion of disturbed pixels on the y-axis, and then the years of the classified disturbance year from the true disturbance year on the x. So 0 on the x-axis indicates that we got the year perfectly correct. So here you can see a lot of variability in these results, but most of our accuracies fall within 40% to 100% accurate in terms of year disturbance. It is interesting here that you can see a difference in disturbance regime. So for instance, Oregon, which is shown here in yellow, has really good classification rates for year of disturbance. And that's probably because most of the disturbances in this area are very discrete. So they're things like harvest or high severity fires. So they're really easy to find and really easy to get the exact year. On the other hand, if you look at somewhere like Colorado, it's shown in orange here, that's a lot lower disturbance accuracy rates. And that's probably because a lot of this disturbance was bark beetle attack, in combination with drought as well. So it's this very gradual disturbance, and it's really hard to pick up the first year that is occurring. All right, so this is, I'm going to show you a couple of the maps that we got out of this. This is southwestern Oregon. So Crater Lake is somewhere about right here. So this is what this looks like. This is actually pretty good. You can't quite see the detail here, but essentially what we're looking at is a bunch of different disturbance event or fire events up here, and then this is all harvest. So just to orient you, disturbance type is indicated by different types of colors here, whereas the saturation of those colors corresponds to the year of the disturbance, with more saturated colors being nearer to our winter time. So this looks pretty good. You can see that we did get some Landsat striping errors here, so a lot of these errors in terms of false disturbance rate is probably due to some pre-processing stuff that we need to work on. Okay, this is another kind of interesting example. This is northern Minnesota, up by Duluth. And this is a very different disturbance regime, as you can see. There's a lot less disturbance, and it's a lot of different types relative to Oregon. The interesting thing that I wanted to note here is that training is really important, especially when it comes to attribution. So what we're showing here is that we sampled along this diagonal from the top left to the bottom right, and we completely missed this big fire that occurred in 2011 up in the far right corner. So it's saying that that's harvest. It's not harvest, it's a bog fire, but we didn't get any fires in the attribution training, so therefore it's misclassified. So probably we need to think a little bit more about how we're training these pixels, especially when it comes to attribution. Okay. So the other thing that I don't have data on, well, I have data but I don't have figures on yet, is looking at this idea that the variables important for disturbance really differ depending on the ecoregion. So we had all these different variables, both relating to single pixels as well as these spatial variables, and that the importance of those variables in both the detection models and the attribution models was not really consistent across these systems. So you had really different variables that were important for models in, say, Oregon and Washington, where you have these very large and discrete events, relative to the variables that were important down here in the east, especially in like South Carolina. So in the west, the variables that tended to be important were these very simple characteristic disturbance variables such as magnitude and duration, whereas in South Carolina especially, the variance in the time series was actually the most important. So if you saw a really big difference in the, say, early variance in the time series relative to the late variance in the time series, that indicated the disturbance had occurred. But that's a much different variable than you're typically looking at when you're looking at these change detection approaches. Okay, so our conclusions with this analysis were that, one, the variable importance really does differ by region. So this is really interesting because most disturbance detection algorithms out there today just apply this change detection approach, where you kind of assume that disturbances look roughly the same anywhere in the world. So this is definitely not true, and I think that we can really improve our ability to detect and attribute force disturbances if we treat them differently depending on the ecosystem type and ecosystem patterns that they occur in. Again, we also are pretty happy with this because this is a new method that achieves pretty similar accuracies to those seen in other products, but it's really flexible. So it's built entirely in R. It can be applied anywhere that you have data. It can be applied to not only Landsat data, but other types of data as well. So it's really flexible, and it also incorporates training. So hopefully we can continue to build on this and have a new product out there. Okay, so shifting gears, this is the question that we're most interested in our current research here at Michigan State. So to this question of how does environmental heterogeneity influence patterns of biodiversity? So the idea here is that the landscape is really, the heterogeneity of the landscape is really connected to the patterns of biodiversity on that landscape. So for instance, you're going to have really different patterns of biodiversity in this mountain landscape in Montana relative to this prairie landscape in North Dakota. So essentially what we're thinking here is that if you have higher abiotic heterogeneity, for instance, topographic or climatic heterogeneity, you're going to have lots of different habitat niches and therefore a lot of differences in functional diversity and total biodiversity. But this really differs according to the scale that you're looking at. So for instance, if you look at really small scales, you might see pretty similar patterns between these two ecosystems. So for instance, you're going to capture a little bit of biodiversity here, a little bit of biodiversity here, but it might not differ that much across systems. Additionally, if you think of the abiotic heterogeneity within the scale, even if you manage to get this little circle over a cliff and you encompass a ton of topographic heterogeneity, you're still not going to be able to pick up that much biodiversity. However, if you then scale up that circle, so let's say now we're looking at, say, 5-kilometer resolution, you're going to capture some really different patterns. So over here on the left, your biodiversity is going to increase a lot because you're now encompassing lots of different habitat niches, and your geodiversity is also going to increase a lot. However, if you look over here in North Dakota again, your biodiversity is probably not going to change that much because it's a fairly homogeneous landscape, and also the geodiversity stays roughly the same. So these scaling relationships can really have big impacts on what you find. So one of the questions that we're looking at right now is how do scaling relationships between geodiversity, or this abiotic heterogeneity, and biodiversity change across both taxonomic and functional groups. So in terms of taxonomic groups, we're interested in how these scaling relationships differ between birds over here and trees. So with the idea that birds are fairly short-lived, they can move around a lot, so they're going to have really different interactions with their landscape relative to trees, which cannot move around on the landscape and are very long-lived relative to birds. Additionally, we're interested in how these scaling relationships change within taxonomic groups, but among functional groups. So for instance, short-lived trees versus long-lived trees. So for instance, a short-lived tree, like a lodgepole pine, is going to be able to turn over much more quickly because it has shorter generation times, and potentially move its habitat a lot more in relation to the abiotic environment. Whereas something that's very long-lived, like a whitebark pine or a bristlecone pine, is going to have longer generation times and not be able to move around in its environment quite as much. Okay, so this is an analysis we're kind of just starting. I'm building off of some work by Quentin Reed, who was a postdoc in Dr. Zanetsky's lab last year. So what we're looking at here is models of biodiversity of FIA data, so forest inventory and analysis data, for short-lived species of trees and long-lived species of trees at varying scales of geodiversity. So if you can imagine down here in this right-hand corner, if this is the FIA plot, very small little FIA plot on the landscape, then we have climate and other geodiversity variables summarized at multiple scales around that plot. So for example, we can have 1 kilometer radii around that plot, and you're summarizing, say, climatic variability of that area, so the standard deviation of climate, for instance. Or you can scale up to a 5-kilometer radius around that plot, and suddenly encompass a lot more variation, which can really affect the amounts of biodiversity you're seeing. Okay, so to break down this figure a little bit, again, this is short-lived trees here. I'll show you long-lived trees in a minute. We did several different models, ranging with varying types of predictors here. We've got climate, geodiversity, and human influence that all have these different scales. So we summarized them at 1 kilometer resolution, 5 kilometers, 20 kilometers, and 100 kilometers around that biodiversity point. And then ran different models with varying combinations of those scales for the predictors. So up here we have the best model on top and the worst model on the bottom. So what we're showing here is that for climate variables, such as temperature or precipitation, the scale really doesn't matter that much. So in the top 5 models, you see a ton of variation in the scale that climatic variable is summarized at. So this indicates that climate at 1 kilometer resolution around the biodiversity point is roughly equivalent to 100 kilometers. You're capturing all that variation. That changes a lot when you suddenly switch to geodiversity, which can include things like topographic variation or variation in soil type or age. So suddenly, all the top models have 5 kilometer radii around that point. And then human influence, it seems to be a very small scale, so 1 kilometer. So this makes a lot of sense if you think about how biodiversity is interacting with the environment. Humans and, say, a trail are not going to be affecting the environment that much more than a kilometer away. So this makes a lot of sense, whereas geodiversity, things like topographic heterogeneity, really can influence biodiversity pretty far away from that one location. So we looked at this in both short-lived trees and long-lived trees. So this is showing the long-lived tree models. And what we're seeing here is pretty much the same thing. So this indicates that the longevity of the species really, or of the group, doesn't really seem to impact how it relates to the scales of these various different variables. So what we're going to be doing in the future is then, again, looking across taxonomic groups, so trees versus birds, and then also within other different types of functional partitions. So we're going to be looking not only at longevity, but also things like dispersal to see if that changes the results. Okay, and then just a brief mention of some future projects here. So the project that we're hoping to start next year is this question, what ability does geodiversity have to buffer biodiversity against global change? So the idea here is, again, if you have higher levels of geodiversity, so for instance, climatic or topographic variability on the landscape, you have more habitat niches in a smaller space. So these species have the potential to move not very far to deal with new types of climate or disturbance regimes. However, if you're looking at a flatter location or a less climatically variable location, those species will potentially have to move a lot more or be incapable of moving to find more appropriate climatic spaces. Okay, and with that, I would like to thank everyone who's worked with me on these projects, including collaboration with here and at University of Montana, as well as my funding resources, NASA and USDA. Thanks.
So what is a short-lived tree species versus a long-lived?
Yeah.
How long is that?
So I think my split here was 200 meters. So I basically just looked at like the range of values that we had in the FIA plots, and it looked like the midpoint was about 200 meters. So that's what we use for now. I don't know if that's like a very good split or not, but definitely need to look into that a little bit more.
In your program in R, what are some factors that you think might be causing it to detect disturbance where there is none? Have you identified some of those factors?
Yeah, for sure. It's actually really fun to look at. So a couple of the things that we picked up, one of the big things is that you can actually have errors in the satellite product itself. So as I mentioned, Landsat scenes can have this banding issue. So I use Landsat 7, which has a scanline corrector issue. So you actually have banding in those images. And so if I somehow didn't deal with that, then you might get a much lower value just due to the fact that it's a satellite error and not due to the fact that there's actually lower greenness. Other things, I wasn't looking for drought in this study. So things like climatic variability can also cause drops in greenness that are not actually vegetation loss or mortality. And then there are a lot of different things. Things like crops cause problems. So for instance, if a forest occurs next to an agricultural area and they plant in one year and then don't plant in the next, that's going to influence the greenness of the forest as well. That's a very big story.
That's really interesting, thank you. There are a couple of things I maybe missed, or maybe you could explain a bit more. So I wasn't sure in where you were talking about assigning different types of disturbances and kind of developing that disturbance and detection algorithm. I wasn't sure what your model accuracy was assessed against. So that was one question. And then the other one was I wasn't sure how you were attributing the different type of disturbance.
Yeah, so I kind of skimmed over that, but what I actually did was, I don't know if you're familiar with time sync. Okay, so it essentially is this product that I recreated in R that looks at both maps of like current day forest scenes, so just satellite imagery of like what it actually looks like, as well as the time series themselves. So it shows like the image from upgraded from 2000 through 2016, and then also shows the time series plot. It's just a line plot. And then if that wasn't clear, what the disturbance type was or whether it was disturbed, I also just looked at historical imagery and Google Earth, which you can usually tell like, what the disturbance is. So I went through and selected random points, classified those, and then used that to translate them.
And so some of the things you're looking at, and you did mention this in your talk, like Bart Beta would be a more gradual disturbance and fire would be more immediate, that kind of thing is what you're using to determine when you're kind of classifying manually these points.
Yeah, but you can also see, so like Google Earth, it's just like actual pictures of the area from, yeah, so you can see a transition from like healthy vegetation to this red stage to the gray stage.
Yeah.
Or the fire occurs, it's very clear. So we were actually like looking at those points using all these different pictures. And that's what I used for validations.
Okay. Okay, so that was what the plot of model accuracy was like looking, okay. Yeah, great.
So kind of bringing your two components of the talk together, so if you added disturbance to these models that explain biodiversity, where do you think, what scale do you think disturbance would be most important? For trees?
For trees? I imagine it would be a pretty large scale for trees, just because you're influencing patchiness of the landscape, so you might get pretty big changes at these very large scales. I imagine, whereas I think it would probably be similar for birds. I'm not really sure.
And so do you think if the type of, attributing the type of disturbance would really kind of differ, or is it just kind of disturbance severity as you sort of suggested this in your work?
Looking at it biodiversity,
Yeah.
I think the disturbance type would matter a lot. So especially for birds, because they're going to use habitat really differently, whether those trees are remaining standing or if they've fallen or burned. So I think disturbance type is really important. Yeah.
When you were looking at the different disturbance types and the amount of carbon released after them, did you look at how long does it take for the forest to bounce back?
Yeah, so we had a pretty short time series. MODIS data is only available since 2000. So I think, yeah, I showed it for 12 years after the disturbance, and you sometimes see a recovery in those lower severity disturbances, but it does tend to stick around for 10 or more years. The other problem there is that productivity is a model product. And so you might get a bounce back in green mist that will look like a bounce back in terms of productivity, but we're really not sure how that corresponds to actual recovery, productivity, and landscape on the ground. But it can take many, many years.
Well, let's thank Amy Cooper.